You know, when you look at a megastructure like the Makkah Royal Clock Tower, it's so easy to just see it as a symbol, right? A landmark. But for this explainer, we're going to peel back the layers and deconstruct it for what it truly is, an absolutely monumental engineering problem. So let's start our analysis right from the ground up. Okay, first things first, let's just get a grip on the physical reality here. The tower climbs 601 meters into the sky. That puts it in a very elite club of the tallest structures humans have ever built. And that number, 601 meters, it isn't just a statistic. It is the fundamental problem statement that governs every single engineering decision that follows. So that's what we're going to do. We're going to get purely technical. We'll be digging into the engineering intent, the why behind the design. We'll look at the incredible structural forces it has to fight every single day and the advanced material science that actually makes it all possible. We're literally going from the bedrock all the way to the crescent at the very top. Right, so where do you even begin with something that's massive? Well, like every super tall building, its life begins deep underground. For the Makkah Tower, the very first, and you could argue the most critical challenge, was figuring out how to anchor a vertical city on a really complex geological site. The solution they landed on was a hybrid system, and it's known as a raft pile foundation. Now, this is really clever. Think of it as two systems working together as one. First, you have this enormous concrete slab. That's the raft, and its job is to spread the tower's colossal weight. But then you have deep piles that punch down through the earth and lock that raft directly into the solid bedrock way, way below. And this table just illustrates that problem-solving process perfectly. The geological constraint? Aggressive, corrosive groundwater. The engineered response? Highly resistant concrete. The problem of the immense vertical load? A 6-meter-thick concrete raft to distribute it evenly. And to battle the overturning forces from wind and potential earthquakes, piles driven 87 meters deep into bedrock. It's all about creating a system with a design life of over 100 years. Okay, so let's start climbing up from that foundation. As we ascend, the tower's whole engineering strategy basically splits in two. It's not an exaggeration to call it a tale of two completely different structures, one sitting right on top of the other. So check this out. From the ground up to 347 meters, the tower is basically a fortress of high-performance reinforced concrete. The whole goal down there is maximum stiffness, maximum stability. But then, above that point, it completely transforms. The structure shifts to a much lighter steel composite and then to a pure steel system. So why the change? Well, this was driven by a game-changing decision back in 2006 to add that enormous clock and spire. The engineers had to figure out a way to add all that extra height without overloading the foundation that was already designed.
And this upper section, this is where the project shifts from just pure structural might to incredible precision engineering. The clock and the spire threw a whole new set of challenges into the mix, all defined by massive scale and the absolute non-negotiable need to minimize weight.
Let's just try to grasp the scale here for a second. Each of the 4 clock faces has a diameter of 43 meters. To put that in perspective, that's wider than the entire wingspan of a Boeing 737 airliner. Now, to move the hands across a clock face that huge, you need some serious power. The drive mechanism for a single clock, basically the gearbox that turns the hands, weighs 21 metric tons all by itself. And to make sure you can see it, well, each face is lit up by 2 million individual LEDs. That's why it's visible from up to 25 kilometers away. It's just an incredible amount of integrated technology. So here's the million-dollar question. How do you build clock hands that enormous without them just collapsing under their own weight? The answer didn't come from traditional construction. It came from advanced materials science. The hands are made from carbon fiber, using a single-shell construction technique borrowed directly from high-performance yacht building. This means they're incredibly strong, yet they're also hollow. You can actually walk inside them for maintenance, and light enough to be structurally viable. It's a brilliant material solution. All right, so you've built this incredibly tall, relatively slender tower. Now you have to deal with its primary antagonist, and it's an invisible one, the wind. Managing the dynamic forces that the wind exerts on the tower was an absolutely central engineering concern from day one. And the strategy to deal with it was a very logical 3-step process. First, analysis. They used extensive computer modeling and physical wind tunnels to understand exactly how the wind would behave. Second,
dissipation. They designed a system of outriggers and belt trusses to basically transfer that wind energy into the building's strong core. And finally, for active control, a 1,000-ton tuned mast damper was installed near the top. This thing is a giant pendulum that physically swings to counteract the building's sway and keep it stable.
So, as we start to pull all these different pieces together, it becomes incredibly clear that the Makkah Clock Tower isn't just one single structure. It's a highly integrated collection of interdependent systems, all working together.
And you know, this chart really reframes your whole perspective. The physical frame, the concrete and steel skeleton, that's less than half the story. A full fifth of the engineering is just dedicated to dynamic control, to fighting the wind. Then you've got the vertical transport, 89 high-speed elevators moving 75,000 people. You have the incredible precision systems of the atomic clocks. And then all the life safety and logistics systems. They all have to work in perfect concert, or the whole thing fails.
There's a quote that I think just captures the unique nature of this project perfectly. It's one of those rare cases where the absolute cutting edge of geotechnics, materials science, and precision mechanics are all marshaled to serve a deeply spiritual and cultural purpose. It's a true fusion.
And that really leaves us with a final thought to chew on. In a project this complex, the lines just get completely blurred. You know, is that tuned mast damper part of the structure, or is it a dynamic control system? Are the atomic clocks just a feature, or are they a fundamental utility of the building? It forces you to ask, when engineering operates at this kind of scale, where does the structure actually end and the system truly begin?
If you're ready to level up, like and share this video. Subscribe and hit the bell to join the future of efficiency. Era, your life optimized.